A single high-bandwidth memory stack sits on the table. It is roughly the footprint of a postage stamp, standing about 1 millimeter tall, and it is integrated directly onto the silicon interposer of every major artificial intelligence accelerator that has shipped in volume over the last 2 years. Teardown reports describe it as a memory component, assign it a bandwidth figure, and move on to the next part. That treatment is accurate as far as it goes, and it does not go nearly far enough. What the stack actually is, taken apart layer by layer, is the upstream cause of a price the laptop buyer felt at the shelf and probably did not connect to a data center component they have never seen. The surface reading says that high bandwidth memory is expensive because it is technically demanding. That is true. The deeper reading, which the teardown reports do not assemble, is that the technical demands of building this stack reorganized an entire industry's wafer allocation, and that reorganization reached all the way down to the commodity end of the market, the memory in consumer laptops and desktops, in the form of constrained supply and elevated prices. The stack on the accelerator and the module in the laptop compete for the same upstream resource. One of them won that competition decisively. The cuts run from the electrical interface at the top of the stack, down through the die arrangement and the through-silicon via geometry, into the process-level commitment those vias represent, then outward to the capacity decisions the three dominant memory makers took when artificial intelligence accelerator demand arrived through the commodity channel that absorbed the consequences, and finally to the competitor that stepped into the vacancy the incumbents left. Every layer returns to the same object on the table. The outermost layer of the stack is what the accelerator sees, a memory interface 1024 bits wide. To put that number in context, the channel width of a standard consumer memory module is 64 bits. The high bandwidth stack is 16 times wider at the interface, and that width is not an engineering preference. It is the answer to a specific physical problem. Training large neural networks requires moving enormous volumes of weight data between memory and compute in a tight latency window, and a narrow interface cannot be compensated for with higher clock speeds beyond a certain point. The physics of off-chip signaling imposes a power cost per bit that compounds with frequency, and at the power envelopes available in a sealed accelerator package, the DDR approach hits a ceiling. The width of the interface is the solution. The bandwidth figures derived from that interface width, independent analyses placing peak throughput in the range of several terabytes per second per stack, based on published specifications from the standards body that defines the interface and from the accelerator vendor's own disclosures, are not in dispute in terms of their order of magnitude. What that interface requires to exist is the next layer down. Below the interface is the physical structure that produces it. Multiple DRAM dies stacked vertically, each thin to well under 100 micrometers, bonded and connected by through-silicon vias. The number of dies in a stack varies by product tier, with configurations ranging from 4 dies to 12 dies according to publicly disclosed specifications from the manufacturers. The through-silicon vias, vertical copper conductors etched through the silicon itself, run through every layer of the stack, connecting each die to the one below it and ultimately to the logic die beneath the package. Their pitch, the center-to-center distance between adjacent conductors, is reported by the manufacturers to be in the range of tens of micrometers for current generation products. That is a fine geometry, and it has to be, because the number of vias required to service a 1024-bit interface across multiple die layers is not small. The vertical geometry exists because the alternative, placing the same aggregate memory capacity beside the processor on a conventional circuit board, would require a signal path long enough to accumulate exactly the latency and power penalty the system is trying to eliminate. The interposer that the stack and the logic die both mount on is typically several hundred square millimeters of area, and even at that scale, the horizontal distances involved are measured in fractions of a millimeter. The stack is tall because it cannot be wide. The through-silicon vias are not simply a packaging convenience, and this is the first observation the teardown data supports but does not explicitly state. Their pitch and density set a floor on the die area each layer must occupy. A via infrastructure with this density requires process steps, masking layers, etch sequences, fill, and planarization that are incompatible with the high-volume commodity flow running on the same process node. A memory manufacturer that retooled a fabrication line to support this geometry did not make a marginal adjustment to its output mix. It made a categorical commitment because the equipment qualified for via middle through silicon via integration is dedicated to that flow and cannot simultaneously run the standard commodity sequence. The duration of that commitment is measured in years, not quarters. This is where the industrial consequence of the stack's construction becomes structural rather than incidental. The process-level commitment maps directly onto a capacity allocation decision. Manufacturing through silicon vias via a via-middle integration scheme, the dominant approach at the leading memory manufacturers for current-generation high-bandwidth products, as described in published process characterizations and working group documentation from the relevant standards body, requires that the fab line incorporating this process be counted separately from the commodity line. When the manufacturers describe their capacity, they are describing two increasingly distinct categories of leading-edge output. The yield impact of through silicon via integration is not publicly quantified by the producers. Analysts have estimated incremental cost contributions, but these figures are projections rather than audited cost data. What is public is the directional commitment. Each of the three dominant memory makers disclosed through earnings calls and investor presentations in 2022, 2023, and 2024 that they were increasing the share of their leading-edge capacity allocated to high-bandwidth memory. The precise percentages are not uniformly disclosed. Analyst estimates from firms covering the memory sector suggest that by 2024, a meaningful fraction of leading-edge wafer starts at the dominant producers was flowing to high-bandwidth memory rather than commodity memory. Several estimates place that fraction in the range of 20 to 30% of leading-edge output at the largest producers. These are analyst estimates, not audited production figures, and that distinction matters for the precision of any downstream claim. The second observation the data supports concerns what the spec sheet does not describe. The specification for a high-bandwidth memory stack tells the accelerator engineer what the stack delivers: bandwidth, capacity, interface width, power envelope. It does not describe what the stack withdraws from the rest of the product line. That withdrawal is not visible in any single teardown. It becomes visible when you hold the stack in one hand and ask where the wafer capacity that produced it came from. The answer, consistent across producer disclosures and analyst estimates, is that a growing fraction of the best available process capacity at all three major producers shifted toward high-bandwidth memory at exactly the moment consumer and enterprise demand for commodity memory was recovering from an inventory correction. The stack on the accelerator and the module in the laptop were never in the same aisle of the same store. They were competing for the same upstream resource, and the accelerator's requirement won because it was worth more per die to the producer. The consequence for the commodity buyer was not an intended outcome of that decision. It was a structural side effect. To make the upstream competition concrete, a leading-edge memory wafer is a silicon disk roughly 300 millimeters in diameter. The analogy to a large dinner plate is not decorative. It is the physical object that imposes the constraint. The number of usable die cut from one wafer depends on die size and process yield. For current generation memory, a single wafer yields dies in the hundreds for a typical consumer-sized die. When a producer commits a wafer to high bandwidth memory, that disk does not yield more silicon. It yields fewer, larger, more complex dies at a higher value per die. Every high bandwidth memory die cut from that plate is a consumer memory die not cut from it. The substitution relationship operates at the level of physical substrate before any market transaction takes place. This is where the competition is decided, and it is not decided by the buyer. The commodity channel received what remained after the leading edge capacity committed to high bandwidth production. Memory used in consumer laptops, desktop systems, and most enterprise servers, the standard double data rate generations that dominate the installed base, is manufactured on the same leading-edge process nodes as high-bandwidth memory dies without the through silicon via integration steps. When capacity at those nodes shifts toward the more complex product, the simpler product competes for a smaller pool of available wafer starts. Memory pricing is historically volatile, and attributing a specific price level to a specific cause requires care. No analyst report cleanly isolates the high-bandwidth memory capacity effect from other factors, including server refresh cycles, consumer personal computer demand recovery, and speculative inventory purchasing by distributors. The directional relationship, leading edge capacity constrained by a structural commitment to a higher margin product, commodity prices elevated relative to prior cycle troughs is consistent with what the producers disclosed and with what the price tracking services documented through 2023 and into 2024. The data is consistent. The precise attribution is not settled. The deepest layer of this dissection is where the vacancy becomes visible. The capacity decisions made by the three dominant producers, rational from a margin standpoint, structural in their duration, left the commodity low end of the memory market underserved. Not abandoned. The producers continued to sell commodity memory, underserved in the sense that incremental leading edge capacity was not flowing there, and the product mix was shifting upward. That vacancy had a consequence the producers did not design for, and a competitor that was positioned to fill it. Chongqing Memory Technologies, operating in China and in volume production by its own disclosure, and by the assessment of analysts covering the Chinese semiconductor sector for several years, has a disclosed product line covering standard double data rate 4 and what the company characterizes as double data rate 5 compatible products. Independent technical assessment of this company's process maturity is not uniform. Some analysts, citing die photographs and process characterizations derived from teardown reports, place the company's effective node capability at a generation or more behind the leading edge of the three dominant producers. Others note that for the commodity end of the market, where the performance ceiling is lower and the buyer is more sensitive to price than to the last increment of latency or bandwidth, that gap is less consequential than it would be in the high bandwidth memory segment. The company does not manufacture high bandwidth memory. By its own disclosure and by all available external analysis, it is not positioned to enter that segment. What it is positioned to serve is exactly the commodity tier that the three dominant producers deprioritized when they committed their leading edge capacity upward. The third observation the dissection exposes is this: the absence of this company from the high bandwidth memory stack is itself load-bearing information. The export controls that restrict access to leading-edge lithography equipment, documented in successive rounds of United States Commerce Department entity list updates and export control rule changes, are the same controls that place high-bandwidth memory production at the leading edge beyond reach for this producer. Via middle through silicon via integration at the required pitch on the required process node with the required yield demands tooling that the export restrictions are specifically designed to prevent this company from acquiring. The restriction is effective at the top of the stack. At the bottom of the market, commodity double data rate 4, entry-level double data rate 5, the process maturity required is within reach of the equipment this company can access. The export controls defined an upper boundary that matched with nearly exact precision the tier the incumbent producers were moving away from. The two constraints operating on different actors produced the same outcome: a vacancy in commodity memory that this producer is now filling at exactly the moment the incumbents are least focused on defending it. This is not a claim that the export controls created the vacancy deliberately. The vacancy was created by the high bandwidth memory stack's own requirements pulling the incumbents up market. The export controls created the condition under which only one category of producer, the constrained entrant, was positioned to serve the tier being vacated. The high bandwidth memory stack did not create this competitor. It created the market conditions that made this competitor's entry into the low-end commercially viable at precisely the moment when the incumbent's attention and capacity were directed elsewhere. Three things the dissection cannot settle, stated plainly. The first is the attribution question on commodity pricing. The analysis cannot isolate what fraction of the price movement in consumer memory from 2023 onward is attributable to high bandwidth memory capacity absorption versus server refresh cycles, inventory corrections, and speculative purchasing. The directional relationship is coherent and consistent with what the producers disclosed, but no independent study has isolated the high bandwidth memory variable with the precision a causal claim would require, and the producers do not publish the production data that would allow external verification of the analyst estimates. The second is the process maturity and market impact of the Chinese entrant. Die photographs and process characterizations from teardown reports are partial evidence. They can suggest process maturity but cannot confirm it. The company's actual market share in commodity memory and the degree to which its production has meaningfully affected global supply conditions is not confirmed by audited shipment data. The company's own disclosures are the primary source, and they are not granular on volumes or yields. The third is the durability of the high bandwidth memory architecture itself. Whether alternative memory approaches, compute near memory designs, next generation low power variants optimized for inference rather than training, or architectural changes in how accelerators stage memory will redistribute demand in ways that relieve pressure on leading edge capacity is a question the current teardown cannot answer. Thermal limits on the stack itself, heat generated by the logic die beneath the memory package, and the limited thermal path available through the interposer are a genuine engineering constraint that the specification sheet does not fully represent, and whether those limits become binding at higher die counts or higher clock rates is an open question. What the dissection does settle is the structural relationship. High bandwidth memory and commodity memory compete at the wafer, upstream of any market transaction, and the capacity decisions made at that upstream point propagate through the market in ways that are real, directionally clear, and imprecisely quantifiable from outside the fabrication facilities. The layers of this stack, taken together, describe one mechanism operating across the full breadth of the memory market. A design optimized for maximum bandwidth density, achieved through vertical integration, through silicon via geometry, and the commitment of leading-edge process capacity to a complex flow, reorganized the industry's resource allocation by pulling the best available wafer starts toward the highest margin application. That reorganization elevated one segment of the market by concentrating the finest available capacity there, and it left the other segment to absorb the consequences and constrained supply, elevated prices, and the entry of a producer the export controls were not calibrated to exclude at that tier. The constraint is legible in the silicon. The high bandwidth memory stack is not simply a memory component with an impressive specification. It is the physical record of a capacity decision that restructured the market below it, in the laptop aisle, at a remove that made the connection nearly invisible to the buyer experiencing it. What the stack proves, layer by layer, is that the most consequential thing about an expensive technology is not what it costs the buyer who chooses it. It is what it withdraws from the buyer who had no choice in the matter. The next object worth opening is the silicon interposer that the high bandwidth memory stack and the logic die both mount on, a component described as passive, but whose manufacturing constraints may turn out to be the next bottleneck the market has not yet priced in. If that is where you want the next incision, name it in the comments, subscribe if you want the next layer.